so I've got to issue a public apology. If you've watched the previous build videos for this 3D printer, this is the real non-sped up speed of the printer. Currently it's embarrassingly slow, so I thought today we'll start making it a bit faster. We're going to do this with the help of a bunch of magnets like these. This will be the first of a few videos in this series focused on automated speed tuning methods. Anyway, speed is somewhat dependent on what exactly we are printing. So for now we're going to continue printing more of these 3D benchy models because who doesn't need more boats in their life? Up to now I've been using Prusa Slicer to generate the G-code files that my printer uses to print this model. If you go into the settings, it comes with a bunch of these speed settings that we can tune. Most likely these are fairly conservative by default since the slicer doesn't know about how specific people built their printers. So naively we can approach the problem of going faster by iteratively fiddling with these settings, reslicing our model and seeing if it went any faster. There are mainly two problems with this. First, there are hundreds of settings in here and I don't know which ones are the bottlenecks to making my print faster. And second, the slicer is perfectly happy with me putting in crazy high values into these fields, but I have no idea what is physically possible for my printer to achieve. To start off, it would be good if we could measure how much time different parts of the print are taking to see if we can then work backwards to which parameters need to be optimized. If you've used these slicers before, you've probably noticed that they already give a time breakdown for different parts of the print in the top left and an overall time estimate in the bottom right. Also, if you ever tried relying on this number, you've probably noticed that it tends to not always be accurate. Fundamentally, how the slicer's time estimator works is as follows. As input, it uses the printer settings in the slicer's machine profile, and it has the generated G-code which looks like this and is basically just a list of the positions and feed rates to go to. The G-code is still several computations away from a time estimate, so that estimator is going to have to crunch a bunch of physics equations to try to simulate what the printer is doing with the G-code. If you watched part 4 of this series, we went over what the printer firmware does with the G-code. The printer has its own separate config file and its firmware will run a bunch of code to eventually generate step times to give to the motors. The time at which the printer's firmware generates the final motor step for the print is effectively the end time of the print. Even if we ignore heating and homing times, there are a few reasons why the slicer won't give us the same result as the printer firmware. First, there's no guarantee that the slicer settings are pulling from the same settings source as the printer's firmware, so there may be inconsistency there if you're using a newer or older slicer or firmware version. Second, the slicer's motion control code is usually a separately maintained codebase compared to the printer firmware's code, so there may be behavioral differences between what the code does. Just as an example, there are at least 3 different ways in different firmwares to handle cornering speeds, and how this is calculated can significantly change the speed for models with a lot of corners. The solution to this is kind of obvious, which is to just run the firmware code when calculating time estimates. The main things you need to change are: first, usually the firmware is running with a real-time clock to pace how quickly it sends commands to the motors. Instead of this, you effectively need to swap in a fake clock that fast-forwards through any time the firmware is sleeping, so you don't have to wait an entire hour to get a time estimate. And second, instead of sending the motions to the motors, we need to save the step commands to a log and check back at the end to see when the final step completes. Note that if you watch my previous videos, we also have accurate physics simulations of the hot end and bed heaters, so we would ideally wire those in as well to get a complete time estimate, but for now I'm going to be ignoring the heat up and cool down times. Anyway, since I'm using a custom written firmware, this is fairly easy for me to do, but fairly boring to look at since the end product is just a command you run, and once it's done running, it gives you a time estimate for the G-code file. The current estimate on screen is pretty high, since the config file for my firmware has all the axis speed limits set to very conservative values, since I didn't know how high I could push them so far. If I bump these up to match what is in the slicer's machine limits and rerun the script, the time estimate gets much closer to what the slicer's time estimate says. If you're using Klipper, as far as I'm aware, no interface has this level of simulation integrated through Klipper. Anyway, I also made my script print out a few more interesting metrics to help guide my tuning of my printer speed. First, this is a table of time spent on the print breaking down by which axes are moving and whether or not we are accelerating or moving at a constant speed. Like I mentioned in a previous video, we are using classical trapezoidal acceleration curves that look like this for every motion. So tuning both the top speed and acceleration will be important since the time we spend accelerating will take away from the time we spend going at full speed. For the current G-code file we are looking at, the biggest chunk of time is spent at some constant speed, so increasing our speed settings should help a bit. Also, based on the second row, 30% of time is spent in acceleration, which implies that either our acceleration limit is very low or we have a lot of sharp corners and we need to see if we can increase the cornering speed. Note that lower down in the list, we only have around 5% of time spent on pure Z moves, so we are going to skip tuning Z for the sake of time in this video. Since most of the time is spent moving in some combination of the X, Y, and E extruder axes, I also did some analysis to break this down by the speeds achieved in each of these constant speed segments. These top few rows show that a big chunk of time is spent running at 40, 10, or 100 millimeters per second in the X, Y directions. These look like the numbers that we saw in the slicer settings. It's also interesting that the extruder rate during these moves is only around 1 millimeter per second, so it seems like the extruder isn't yet the bottleneck, though I'm not sure yet what qualifies as a big number for extruder speed. There are also other rows at random XY speeds, which I'm guessing is due to the need to slow down before entering corners, so at some point we will need to figure out how fast we can go around corners. Let me know in the comments if anyone has some other ideas for how to visualize the raw printer motion data. So now we have a rough idea of what to tune, and now we just need to figure out where the limits are. While I'm here dry running all the firmware code, it's worth pointing out that if I rerun this script and time it this time, it takes around 2 seconds to fully process this 1 hour long file. This code is still fairly poorly optimized, but the important takeaway is that 2 seconds is much smaller than the print time, so the host side software probably won't be a bottleneck. To more specifically confirm this, we need to know a little bit more about how the firmware works. Suppose at time 0, our firmware has received all the raw G-code motions it needs to run. It'll schedule these to start running 100 milliseconds in the future so that it has time to send the motions to the microcontrollers before the motions have to occur. The host will run all the math to calculate all the individual step points, and these will be placed into a queue on the microcontrollers. The microcontroller has limited memory, so this queue in my case only has 1000 steps per motor configured right now. Then 100 milliseconds into the print, the queue will start being emptied as motions finish running, and simultaneously the host will be calculating more steps that need to run in the next 100 millisecond long cycle. So important observations from this approach are that first, every single 100 millisecond long segment of our motions needs to be processable in less than 100 milliseconds of host compute time. And second, each 100 millisecond long segment of our motions needs to result in less than 1000 commands to the microcontroller, otherwise we will overflow its memory buffer. Even if on average we are below these limits, we could have crazy segments of motions with a lot of turns that result in a lot of commands needing to be sent. This is fairly easy to verify by logging more metrics in our simulation. In my case, I already did this and we get a result of less than a millisecond peak computation time per 100 millisecond cycle and 173 commands overall per cycle, or 72 per the fastest motor. Note that if you intend on trying to run all the motion planning logic on a slow microcontroller, then measuring these numbers more precisely would be more important. Klipper does a lot more computation than what my firmware is currently doing, so if you're using Klipper, you may find it useful to check out this host benchmark command on their documentation page, though I'm not sure if it'll give you a detailed breakdown like the one in this video. Anyway, based on these numbers, we have headroom on the host side to at least 10x our speed without running into any issues. But wait, we also have software running on this puny microcontroller board that has to drive all the motors, so if we're going to have a bottleneck, it's probably going to be on that. The microcontroller is mainly doing two things that take processing time. First, it's going to be periodically receiving and responding to commands sent by the host machine. And second, it needs to be constantly flipping the signal being sent to the motor drivers, causing them to spin. Note that the intensity of this work mainly depends on the max speed reached. As the speed increases, the time gap between the pulses to the motor will decrease, meaning our microcontroller will need to flip the pin more times every second. This also means that we will finish more motions every second, so the host will probably send the microcontroller more work every second due to the time savings of higher speeds. To test the performance of my microcontroller, I have this separate USB dongle that uses the same microcontroller as my motion control board and has been flashed with the same firmware. You can also do this with the actual motion control board, but it's best to unplug all the motors before actually doing this and setting up all the peripherals to use dummy pins so you don't break anything in the real world. To test how many commands our microcontroller can process, I have a script that will just flood the microcontroller with as many commands as possible, and it will count how many of them get responses every second. The script looks like this when I run it, and I get a result of around 40,000 commands per second. I also had it log the microcontroller's CPU utilization, and it doesn't hit 100%, so probably there is a bottleneck in my host side code if we want this to go any faster. Klipper calls this a command dispatch benchmark, and as you can tell from their reference results, my results are relatively bad. This is due to most of my code being more usability optimized than performance optimized at the moment compared to what Klipper is doing. If you recall the previous test we did, we found that the default slicer speed only requires around 200 commands per second, so unless we want to disable step compression in the future, we don't need this to be any faster. The second thing to test is the max speed we can achieve when generating the step pulses. Testing this is slightly more complicated since we will need to test multiple times at different speeds using binary search to find the fastest speed at which we don't get timing related errors. Timing errors in my firmware and in Klipper generally imply that by the time the microcontroller finished doing all the processing for the next step to be pulsed, the next step time is already passed or is too close for us to reliably enqueue to be triggered. The end result I found for my microcontroller is a minimum limit of around 120 ticks per step, which for my microcontroller's 16 MHz clock means around 130,000 steps per second combined across all the motors. Put that in perspective, my X and Y steppers are currently configured for 80 steps per millimeter, so that puts the peak speed at around 1600 millimeters per second using a single motor, or around 800 millimeters per second conservatively if we divide the budget between the two XY motors. For any software engineers in the audience, these 100 or so ticks are basically just running around 100 lines of code, so you have to do a bunch of tricks like getting rid of as many bound checks and unnecessary operations as possible to get it to run relatively fast. This number is the main reason I kept the speed relatively low up to now, since after the last video I had to do a lot of code optimizations behind the scenes to get it to work this well. If you are using Klipper, there are similar sets of commands you can use documented here for benchmarking your microcontroller's stepping performance. So unfortunately now we have to deal with the real world. We now know that our host computer can go super fast and our microcontroller should be able to send step pulses to our drivers pretty quickly. The next unknown in the chain is how quickly these drivers spin these motors. For simplicity, let's start by assuming that we just have one isolated motor like this with a dummy load on it and a standalone test circuit like this to drive it. At very slow speeds, if we spin it, we expect the real position of the motor to fairly accurately mirror the position that we requested the motor to be at. On the other extreme, once we cross the max speed of the motor won't be able to keep up, so you'd expect these two lines to no longer line up. And you'll probably see and hear this in the form of skipped steps. The classical technique to finding the top speed involves gradually ramping up your speed until you notice your motor skipping. Normally you need to manually listen for skipping, but there are some scripts like this one which will rehome your printer after every test run to see if there was a shift in the homing position. These techniques mainly help with identifying if you have skipped greater than one full motor step. My machine is calibrated for 80 microsteps per millimeter with 16x microstepping, so 80 divided by 16 equals 5 full motor steps per millimeter. So if you skip a full step, you are basically skipping 0.2 millimeters. So if you just set your max speed to say 90% of this limit, you only really know that your error will probably be less than 0.2 millimeters, but you don't know how much lower it is. If you're trying to make dimensionally accurate parts, it's not a particularly good bound, so ideally we find a more precise measurement method. In general, my goal is to come up with an automated test which can do the following. First, it should be able to evaluate sub-step accuracy of our motions. My general target is to ensure there is less than 8 microsteps of error, which equates to around 0.1 millimeters of error. Second, I want to be able to measure the behavior of our motions along all points along the motion and not just the start and end positions. And third, I want it to be fast, which means avoiding the slow step of rehoming the printer to determine if there was a shift in position due to motor skipping. Observant viewers may have already noticed that there's a second wire going off screen from the motor that I've been using to generate all the graphs in this section and will help me achieve these goals. So let me go back and show you how I built that. It all starts with some of these disc magnets. These aren't regular magnets though. If you take some regular neodymium disc magnets, they will stick together the strongest like this because they are axially magnetized. This means that one side of the disc is the north pole and the other side is the south pole. Meanwhile, the magnets we'll be using are diametrically magnetized, meaning that half of the disc is the north pole and the other half is the south pole. So these stick the strongest together on their edges. If you try manually pushing them along the edge, you can tell they are magnetized like this, since you'll notice that they will always snap back to the same angle. Also, if YouTube hasn't compressed away the detail, you may have also noticed that these magnets are a different color compared to the regular magnets. Regular magnets you find are usually made of neodymium. Standard neodymium grades like N52 will start to lose magnetization when heated above 80 degrees Celsius. Since motors tend to get hot when running for a while, we can't put these close to the motor without a risk of failure. Note that there are several grades of neodymium. There are higher temperature SH variants that you can get, which have a temperature rating of around 150 degrees Celsius. From what I can tell, it's a bit annoying to find off-the-shelf magnets that are both high temperature rated and diametrically magnetized in a wide range of sizes. The magnets I'm using I found on DigiKey and are made of samarium cobalt. These magnets are a bit weaker than the neodymium ones, but have an extremely overkill operating temperature of 250 degrees Celsius. Let me know in the comments if anyone knows of any other good supplier of high temperature diametrically magnetized magnets. Anyway, we are going to be mounting one of these magnets to the bottom of our motor's shaft. Since the magnet is diametrically magnetized, this means that if we spin the shaft of the motor, the orientation of the magnetic field below the magnet will also change. In this clip, I marked the magnet with a marker just so you can see it spin, and you can pretend that the black mark is the north pole of the magnet. To go along with this, I made a super simple board that basically just has this magnetic field angle sensor on it. You can basically just think of this as a compass. If you spin a magnet over the sensor is able to tell you which direction the magnet is pointing. Just note that we are going to be reading from the sensor extremely fast, so you generally don't want to run long non-shielded wires back to the main control board from this to avoid electrical noise. So instead I just mounted a microcontroller board to the other side, which we can talk to over USB, which is much more robust at longer distances. So the final setup is going to look like this, where I'm attaching the sensor board below the motor to read the shaft angle. The 3D printed parts are designed to maintain a reasonable air gap to the magnet so that the magnetic field isn't too strong or too weak to sense. For those folks that know what these are usually used for, I should mention that at least in this video, we are not going to be building a closed loop motor controller like the O drive. In general, it's a somewhat orthogonal problem and still requires us to have some instrumentation set up to evaluate the final driver performance. Also, you can get higher precision capacitive encoders like this, but these are a bit bulkier and more annoying to set up since you need to get double shafted motors like these to mount them well. Anyway, if you just try measuring the raw output of the sensor, you'll get data that looks like this. The blue line is the target step position, and the red line is the measured angle from the sensor. Most of these sensors don't keep track of how many revolutions you've done, so whenever you hit 360 degrees, they're just going to go back to 0 degrees. So you need to write some post-processing software to keep track of that, and then once you correct the data, the two lines will line up like this. It's a bit hard to notice, but there are two lines in this graph since they almost perfectly overlap. This is expected if we were going at low speeds, but actually there is a quantifiable difference between these lines. To better visualize this, I'm instead just going to show the error between the two lines by subtracting one from the other. At first glance, this just looks like noise, but something crazy happens if instead of using the time on the x-axis, we use the angle of the magnet reported by the sensor. If you do that, it looks like this. This is data from several rotations of the motor, and you'll see that there is a fairly predictable curve that is being added to all of our measurements. There's mainly three reasons this exists. First, we may not have perfectly aligned the magnet to the center of the shaft of our motor. Second, our sensor board might not be perfectly aligned with the center of the shaft. And third, our sensor isn't perfectly manufactured. If you're a datasheet enjoyer, this third source of error is typically documented in the sensor datasheets and is up to 0.8 degrees for our sensor. The general expectation from the manufacturer is that if you need high resolution measurements, you need to correct for this later in software. Anyway, for our data, we can do this by fitting a best fit curve to the error. Obviously, a single best fit line won't work for this data. So instead, we're going to be fitting a Fourier series, which if you look up on Wikipedia has an equation that looks like this. This looks very complicated, but basically just means we will fit a big sine wave to capture the general shape of the data, and then on top of that, we will gradually stack more smaller amplitude sine waves to closer fit the curve. Once you have this function, whenever you measure a raw angle from the sensor, you would plug it into this curve and add that correction factor to the raw angle before using it. With all that in mind, here's a quick summary of the performance of our sensor. Note that I've normalized all these numbers to be microstep units, so values below 16 mean that we were able to get sub-full step resolution when moving. The first row is the standard deviation of the error when the motor isn't moving, so there is around 0.3 steps of noise just from the sensor and environment being imperfect. Then if you are moving, then the standard deviation is around 2 steps if you don't do anything to the output of the sensor. But if you apply the best fit calibration we just talked about, the error will drop to around 0.49 steps. This is likely higher than the 0.3 value at standstill due to vibration of the motor. Now, in order to find the max speed of the motor, we just need to do some test spins and keep increasing the speed until we have too much error. The graph on screen is the angular error over the course of each test. You'll notice that it tends to get higher on average as the speed increases. Before someone asks, it is not due to there being a time offset between the measurement time and motor step time. The second half of the part 5 video in this 3D printer build series explains why there is effectively zero latency in our system. The reason is instead that the motor isn't producing enough torque to maintain its speed well, so is lagging behind the target position. There are a lot of other parameters that you can tune, like the motor current and voltage, to improve this. Here are the results with the speed on the x-axis and the average error on the y-axis. I did this test using both 5 volts and 12 volts of power to the motors. At 5 volts, the motor starts skipping more than one full step above 75 millimeters per second, while if we crank up the voltage, we can reach higher speeds at lower error. So I think this is kind of a neat way of visualizing how more power can solve this problem, though it may introduce other problems not shown in this graph. Another takeaway here is that even if we aren't close to the max speed of our motor, you can still experience several microsteps of error depending on how well your motor driver is tuned. There do exist other tools like this for tuning your stepper driver's parameters, but for this video I'm just going to be focused on how to measure if a certain set of parameters is good. Tuning additional settings ends up being pretty straightforward since you just need to brute force test them once your way of measuring performance is automated. Now we're going to take what we learned and apply it to the real machine. To do this well, what we've learned is that first we need to ensure that the magnets are as perfectly centered as possible so that we need to do less corrections later. To do this, I 3D printed these magnet holders which keep the magnets perfectly centered in the hole on the back of the motors. Just be aware that you can't print a perfect circle like this without a seam, so I had to do some light sanding of the inner seams with a file to make sure the magnets fits. We will also need to use a strong glue to attach the magnet to the shaft to make sure that the magnet moves perfectly in sync with the shaft. Regular glues like these only have a max operating temperature of around 80 degrees Celsius, so it's risky to use these for this application. Instead, I'm going to be using this JB Weld 2-part epoxy, which has a max operating temperature of around 260 degrees Celsius. Just know that this stuff is basically permanent, and you will break your magnet before you break this epoxy if you try taking off the magnet. To apply it, you first need to mix roughly equal parts of both tubes, and then I'm using a small toothpick to apply a tiny amount of it to the motor shaft before inserting the magnet. You ideally want a very small drop in the middle so that when it flattens and spreads out, it doesn't go inside the motor and messes up the motion. Ideally, you do this before building your printer since there isn't a lot of space to work now. In the end, it'll look like this, and we need to wait 24 hours for the glue to dry before removing the green magnet alignment piece. For anyone who is wondering, all the data shown in this video is with the magnet near perfectly centered and glued with these techniques, so you shouldn't expect to be able to get rid of all the non-linearity. Anyway, once the glue dries, we can mount the encoder board. I'm going to first loosen the tension on the belts, then I'll need to move the electronics out of the way in order to be able to reach the motor screws with a screwdriver. Now I can unscrew 2 of the motor screws, and I'm going to replace them with slightly longer ones to mount the encoder board with a 3D printed spacer. Note that we want this to be as rigidly coupled to the motor as possible to minimize error. I only made one of these encoder boards, so for now, I'm mainly going to be testing diagonal motions involving one motor. So the tests are basically just going back and forth using just one motor at increasing speeds. In theory, for the core XY motion system like this, the speed limit we determined here should be lower than what is possible with both motors moving in other directions. Anyway, after we've done all the test runs, here's the final data. So I was kind of surprised that the error is basically always over 10 microsteps. Then I realized that I've been using the StealthChop setting in my drivers. This is the same setting that push-up printers use for their stealth mode and is supposed to make the motors quieter, though it does reduce accuracy by quite a bit, and even the Klipper documentation recommends disabling it. Anyway, I disabled it, and after rerunning the test, the red line here shows the results with the default spread cycle mode. It's much better now, but unfortunately I can't get it to stall just with increased speed since my microcontroller isn't fast enough to drive it any faster. Also, if you are wondering why the graph is zigzagging up and down, I did consecutive tests in opposite directions along the same diagonal, so it seems like my motion system isn't behaving perfectly symmetrically. If you wanted to, you could also do this same type of test and sweep the acceleration setting at a constant speed. Here's what my mean error looks like at different acceleration levels. It's a bit harder to evaluate this though, since if you just look at the raw error plots over time, you will notice spikes in error during the acceleration period like this, so the mean metrics don't make a lot of sense. At least for my machine, around 4,000 millimeters per second squared of acceleration is the max I can do without exceeding my error targets just in terms of motor position error. What you should be aware of though is that all the testing so far ignores the fact that our machine is using belts to drive the tool head. Intuitively, belts should act like springs, so when they start accelerating, they will stretch a bit and oscillate before actually moving the tool head. So if we accelerate very quickly, they will likely introduce additional lag and positional error beyond what we can observe on the motors. Note that the motor testing should be valid for max speed tuning, since at a constant speed, the forces being applied to the tool head and belts should be significantly lower. But the acceleration limits we get from motor testing can't be trusted. I'm going to be skipping proper acceleration optimization in this video and doing that in a separate video once I finish over-engineering the input shaper in my firmware. In this video though, I thought I'd also make an attempt at measuring the max speed of the extruder. The extruder is also using a stepper motor and doesn't have belts to deal with, but based on my past experiences, I don't expect skipping steps to be the only issue here. As you may remember, here's the internal view of the extruder, which uses gears on the motor to pull the filament through. A fairly common failure mode that I've seen is that instead of just stopping when moving too fast, the gear will just keep spinning and eat away at the plastic filament. So when you take out the filament, it's pretty common to see that the filament got chewed down and the extruder lost grip of the filament. So measuring the extruder motor angle is probably not going to be sufficient to get a foolproof measurement. The traditional way I've seen to solve this problem is to just print out some blobs of filament at different speeds and measure the weight of each of them manually to see if less filament is extruded at high speeds. This seems like a lot of work, so we're going to find a more automated way of doing this. Since this video is about magnets, I got one of these Duet 3D filament sensors. Internally, these work on a similar principle to the motor shaft encoder, except we'll measure the rotation of a gear touching the filament ahead of the extruder. So basically, we will place the filament sensor above the extruder but still in line with the filament. Since the filament sensor's gears aren't being actively driven, the filament is moving, the filament sensor will spin, but if the filament stops moving, the filament sensor will stop moving even if the main extruder gears are still moving. I mainly bought this existing filament sensor to avoid dealing with self-sourcing the right gears and getting the geometry and tension right for gripping the filament. The only thing I don't like about these Duet 3D sensors is that they have this microcontroller board that has its own custom serial protocol which doesn't expose the raw timing measurements from the sensor. Luckily, this thing is open source, so I made a custom board that has a standard quick connector that I can use to directly interface with the sensor. In this case, the data rate doesn't need to be very fast, so using a long cable is probably going to be fine. The whole thing can then be mounted on the back of the printer using the nuts that we pre-inserted way back in part 1 of this video series. Finally, we'll need to start using a proper PTFE tube between the tool head and sensor to keep the movement of the filament coupled between the sensor and extruder. For calibrating the sensor, I'm just going to extrude 100 millimeters of filament at a relatively slow speed and measure how many degrees the sensor reports to have moved. We shouldn't need to do full non-linearity calibration of this sensor. Then we can do the flow rate tuning by extruding filament at different speeds and measuring how many degrees of rotation we observe at each speed. Here's what the data looks like at the end. At all the speeds in the first column, we asked the extruder to extrude 100 millimeters of filament. The second column is the number of rotations that the filament sensor measured. Since we requested the same amount of filament in each run, all the values in this column are supposed to be the same if the extruder actually extruded the same amount. Based on this, we'll assume that we extruded the correct amount at the slowest speed and calculate the relative percentage extruded to generate the next column. Then, since we know the diameter of our filament, we can convert the speed in percentages to flow rates. If you're not a numbers person, here are some graphs. First, here's how the flow rate increases with speed. As you can see, it peaks at around 37 millimeters cubed per second at 17 millimeters per second of speed. And this second graph is the flow percentage versus speed. You can think of this as how much was actually extruded compared to what was asked for. So this second graph shows that we start slipping around 10 millimeters per second of speed. So 10 millimeters per second is the max speed we can go at without slipping, but we can go faster up to 17 millimeters per second if we compensate for the under extrusion. I'm just going to use 10 millimeters per second as the target max speed, which equates to around 23 millimeters cubed per second of flow rate. Also, a quick FYI that even though we can extrude at this speed, we don't know if the fans on our print head are powerful enough to cool down the plastic at this rate, so more testing will be needed for that in the future. Anyway, I found this calculator online that then lets you convert from flow rate to print speed. So according to this, in order to fully utilize the flow rate, we need to be going at 322 millimeters per second in the XY directions. As we tested earlier, we can go way faster than this, so during printing, our limit will be around 300 millimeters per second. Last thing I should mention is that you can get cheaper filament run-out sensors like this one, which you can hack to achieve the same result. If you look inside these, you'll usually find this optical slotted ring, which measures rotation based on how many times an LED passes through these slots. These cheap ones are much less precise than the magnetic encoder that I'm using, so you may need to extrude more filament to get a good result. Anyway, so I've started a new benchy print in the background with all the settings we've found so far. All this footage is 1x speed. Just to summarize the current state, for travel moves, I'm going to allow the printer to move up to 600 millimeters per second in XY. But for printing moves involving the extruder, we are limited to 300 millimeters per second. And for now, I'm using 4000 millimeters per second squared as the acceleration in all cases, though eventually I'll boost this for travel moves. Also, to achieve dimensional accuracy with these settings, I've disabled StealthChop. The final time estimate for this benchy is around 47 minutes with these settings. And here's the final benchy. It looks basically the same as my previous attempts, but took much less time to print. Okay, so now we're going a bit faster. Obviously, this isn't close to world record speeds, but if I made it faster right away, I wouldn't have much to do for the remaining 6 or 7 videos in this 3D printer build series. Anyway, in the next part, we're going to finish making my printer look like it's not half assembled, and I'm going to finish open sourcing all the documentation for building this printer. Surely there will be no over-engineering in the next video. Bye!